Building for mobile seems pretty straightforward, doesn't it? Just shrink the screen, make the buttons bigger, and you're good to go. But what if I told you there's an invisible tax you're paying on every single network request? A tax that's secretly draining your users' batteries and making your app feel slow or even broken. Okay, let's get right into it. Mobile networking is so much more than just web development on a smaller screen. It all comes down to the fundamental physics of how radio waves work, and, more importantly, the constant battle to save battery life. These things create a unique set of rules that can absolutely crush your app's performance if you don't know they exist. So in this explainer, we're going to pull back the curtain on these hidden costs. We'll start with what I call the invisible mobile tax. Then we'll dive into the radio's dimmer switch. We'll talk about why your app needs to stop making small talk with your server, cover the price you pay for just basic protocol overhead, and finally, we'll look at the sneaky and costly energy tail that drains power when your app is doing absolutely nothing. All right, first up, the invisible mobile tax. Most of us think the big mobile challenge is just making a pretty responsive design. But the real fight? It's this constant three-way tug of war between how the app looks, how fast it feels, and how long the user's battery lasts. If you mess up any one of those, the whole experience just falls apart. This is where all our assumptions from the desktop world start to fail us. So let's get into our first hidden cost, what I like to call the radio's dimmer switch. Now, this is a really clever system that was designed to save battery, but it has this huge side effect. It adds a ton of delay. And at the heart of it all is something called the RRC state machine. So here's the easiest way to think about this. Imagine your phone's radio is like a light bulb with a dimmer switch. To save power, your phone automatically dims it and eventually turns it off completely when you're not using it. But the second your app needs to send or receive data, that switch has to turn and the light has to ramp all the way back up to full brightness. That ramp-up time, that is the hidden tax you are paying in pure latency for every single request. Now, technically, this dimmer switch is called the Radio Resource Control, or RRC, state machine. And for every single data transfer, it goes on this little four-step journey. First, it starts in idle state. The radio's off, saving battery. Awesome. But then your app needs something, so it has to go into the transitioning state. This is where the network has to find and allocate resources for you. This step is pure, unavoidable delay. Only after that's done can you get to the connected state, where your data can finally flow. And then, and this is the kicker, after the transfer is done, it enters what's called the tail, where the radio just stays on at full power for a few more seconds, burning energy, just in case. And the cost of just waking up? It's just staggering. On a good 4G LTE network, you're losing 50 to 100 milliseconds before a single byte of your app's data has even been sent. But look at 3G. That can be up to 2.5 seconds. Think about that. The user taps a button, and for 2.5 seconds, literally nothing is happening, except for the radio negotiating with the cell tower. So what about the battery cost? Well, a really simple polling mechanism, something that just wakes the radio every minute to check for updates, can chew through about 3% of the entire phone's battery capacity every single hour. And that's just for one app. It is truly death by 1,000 cuts. It's why just 2 or 3 chatty apps can absolutely kill a phone's battery before lunchtime. So, from a senior engineer's point of view, this forces a few tough reality checks. That set interval function you love to use for polling, it's a battery vampire on mobile. That instant loading spinner you show, well, it's basically a lie if the user is sitting there waiting 2 seconds for the RRC transition to happen first. And the most painful part? A single poorly behaved third-party analytics SDK can make all of your careful optimizations completely worthless. Okay, so if every single request forces the radio to wake up and pay this big energy tax, the solution seems obvious, right? Make fewer requests. And that brings us to our next big idea: stop making small talk. It's all about fighting the chattiness of your app with smart request batching. This is the key takeaway here. There is no such thing as a small request on a mobile network. Think of it like ordering food delivery. If you order a taco, and then an hour later you order a burger, and then later you order some fries, you're going to pay 3 separate delivery fees. But if you order them all at once, you pay 1 fee. Every single network request your app makes pays that RRC delivery fee in both time and battery. And the difference is just night and day. Look at the left side without batching. Each of those 3 requests has to pay the full RRC wake-up cost, and each one triggers its own long, wasteful energy tail. But on the right, when you batch them together, you only pay that RRC cost 1 time. You get 1 single consolidated energy tail. The efficiency gain here is just enormous. But of course, it's a trade-off. It's not that simple. Batching is fantastic for saving battery and making the network more efficient. The big con, though, is that it adds latency to your data. You can't tell a user to wait 5 seconds after they hit send message just so you can batch it with something else. So the senior engineering strategy is to be smart about it. You separate your requests. Critical user-facing actions go out immediately. Deferrable background tasks like analytics or logging, those get batched up and sent later. So let's say you've done all that. You've batched your requests, the radio is fully awake, but the taxes don't stop there. Nope. We still have to pay for protocol overhead. These are the fixed costs that are just baked into the foundation of the internet, and they create what's known as the 600 millisecond problem. Just look at this stack of unavoidable taxes you pay on every single simple HTTP request. First, you pay the RRC negotiation tax to wake the radio. Then you pay for DNS lookup, then a TCP handshake, then a TLS handshake for security. And only after all of that does your actual HTTP request even get sent. Each of these is a separate round trip that just adds more and more latency. Now let's put some hard numbers to it. Even on a fast 4G network, the total overhead before your server even sees the request is between 350 and 600 milliseconds. More than half a second is just gone, wasted. And on 3G, we're talking up to 3.5 seconds of overhead. This is latency that you simply cannot fix on your server. It doesn't matter how fast your backend is. So how do senior engineers fight back? They use smart architectural patterns. They reuse connections with things like keep alives to completely eliminate the TCP and TLS handshakes for later requests. They avoid waterfalls, where one request depends on another, by using patterns like a backend for frontend or GraphQL to get all the data they need in a single trip. And most importantly, they decouple the UI, giving the user instant feedback while all this network nonsense happens in the background. And that brings us to our final hidden cost, and honestly, this one is the sneakiest of them all, the costly energy tail. This is all about the battery your app wastes after it's already finished doing its work. Here's the analogy. Imagine you get home and park your car, but you leave the engine running for another 10 minutes, just in case you need to drive again soon. All that wasted fuel? That's the energy tail. Mobile networks do the exact same thing. After your data is done transferring, the radio stays in a high-power state for anywhere from 5 to 30 seconds, just burning battery for absolutely no reason. And you might think this is just some abstract idea, but it's not. It's very real. Tools like AT&T's Application Resource Optimizer, which you see here, actually let you see this waste in real time. You can literally watch the little bursts of data transfer followed by these long, expensive energy tails where the radio is just burning power while doing nothing. This table is really all the proof you need. Look at the energy cost for one single request. 10 joules for the RRC wake-up, only half a joule for the actual data transfer, but a massive 25 joules for the tail. The tail costs more than everything else combined. Now look at 5 batched requests. The transfer cost goes up a bit, of course, but the RRC and the tail costs, they are identical. The total energy to send 5 times the data is barely any higher than sending just one request. The tail is the real energy monster here. So a senior engineer thinks about this stuff strategically. They know that the common myth of needing constant pings to keep a connection alive is just that, a myth that absolutely kills batteries. They know that testing on the perfect office Wi-Fi is a huge blind spot because the energy profile is 5 to 10 times better than on a real cellular network. And they know to offload big transfers to Wi-Fi whenever they can, saving both the user's battery and their data plan. You see, all of this just goes to show that mobile isn't just a smaller version of the desktop internet. It's a fundamentally different and often hostile environment. Every single choice we make has a real cost in latency and battery life. Which really leaves us with one critical question to ask ourselves. We know our app works great under the perfect conditions of our office Wi-Fi, but is it truly resilient enough for the real world?